Today's lecture is on sorting techniques. So, as part of your data structures course, we study different techniques which we can use to sort elements in a list. The list can be an array or a linked list. In your C programming course, you must have done at least one of these techniques where you sort a list of elements in an array. Okay, so the first sort that I'll discuss with you is going to be heap sort. Since we just finished heaps, this is an easy carry forward. I already explained how we can sort in a heap. We'll just do a recap of that. Okay, so once you have a heap, which is a binary tree, a complete binary tree except for the last level, which can be partially filled. It can be a min heap or a max heap. If it's a max heap, the maximum element of the heap is going to be at the root, and if it's a min heap, the minimum element of the heap or of the list is going to be at the root. So if you want to sort in ascending or descending order, you can take a heap. So you are given a list of elements. You'll take the list of elements. You will create a heap from this list of elements, and then you will delete the elements one by one. So when you delete in a heap, the deletion happens at the root. So you take out, let's say if it's a max heap, you take the max heap out, you take the maximum element out, and you store it. So you either store it in another temporary array, the sorted, which will be your sorted array at the end, or you can store it at the last location in the heap, which I have explained in the heap lecture. Okay, the size of the heap is reduced by 1 and the element is deleted, which is the max element. So you'll get in descending order if you store this max element in another heap. The next maximum will be stored in the second as the second element of the temporary array, and so on till you get a sorted list. The second technique is bubble sort, which you must have probably done in your C programming course. So what does bubble sort do? It compares your adjacent elements. Okay, so if you're doing in ascending order, if the first element is larger than the second element, we will exchange it. Okay, so I'll go to the example straight away. So if you have 5 elements, so in your one round, you will compare all adjacent elements. So that means I'll compare element 0 with element 1. Just a second. So if they are not in order, I need ascending order. So 11 and 15 are in ascending order with respect to each other. Then I'll compare 15 and 2 as I've marked in orange. So 2 should be before 15. So we will swap the 2. Okay. And then I'll continue. So once I swap, this is what I have currently. And I will compare the second element with the third element, which is 15 and 13. And again, they are not in ascending order. I will swap. So I'll come here. Now 13 and 15, 15 and 6 is the last comparison in this round, and again I will swap them. So at the end of first round, so the first round is that I move from element at location 0 to element at location n minus 1. So I compare all the pairs of elements that I have along the way, and I get a order, but this is not yet sorted. So you'll see at the end of every round, the last element, the maximum element in case of ascending order, will move to its correct position. So 15 should have been here. So if you see, 15 was at location 1 and it moved from location 1 to location 4 at the end of the pass. So the maximum element is actually shifted or bubbled to the last location. Okay. Then round 2, again we do the same thing. You compare adjacent elements. You compare 11 and 2. They are not in ascending order, so you will swap. Then 11 and 13, they are in proper order. Then 13 and 6, so you swap, and then you get this. And in this round, you swap 13. You compare 13 and 15, so they are in order. So now you see the second maximum element is at its proper location at the end of round 2. Okay, moving on to round 3. So in case of bubble sort, if you're sorting 5 elements, you will have 5 such rounds. It is possible that your array is sorted well before 5 rounds. That depends on the location of the elements. And but in case of bubble sort, in every round you compare all the pairs, and there are 5 such rounds in case of 5 elements. So round 3, again you compare 2 and 11. You no need to exchange 11 and 6, so you have to exchange. We come here, then you compare 11 and 13. They are in order. 13 and 15, they are in order. So again you see the next maximum, which is 11, has reached its proper location. Then round 4, compare 2 and 6, no exchange. 6 and 11, proper order. 11 and 13, proper order. 13 and 15, so no swapping. Round 5, again there'll be comparison, so it's already swapped at round 4. So if in any round you get to know that there was no swapping, you can stop. So there should be some way in the program which will tell you that there was no swap in this round. That means it is already sorted, so you can exchange. So a simple bubble sort algorithm will have a double for loop, and in the inner loop you'll compare all the adjacent pair of elements, and then the outer loop will do the same thing 5 times. So that is a simple bubble sort algorithm that you can write. But to improvise on our algorithm, we can do two things. One is, if we can find out when to stop, when if in a particular round there was no swapping, we should not continue if there are any more rounds left after this. That is one thing where we can improvise. And the other one is, if if you notice, I told you that at the end of every round, the last element, in let's say in case of ascending order, the maximum element reaches its proper position. In the second round, the second maximum 13 reaches its proper position. In the third round, 11, which is the third maximum, reaches its proper position. So in every round, after we know that 15 has reached its proper position, we don't need to compare 6 and 15. Okay, we are comparing 13 and 15 here. We can as well leave out the last element comparison. We'll just see that in the code that follows. Okay, so a simple bubble sort algorithm, we have some variables: hold, j, pass, and switched equal to true. So if there is swapping that is taking place in any round, switched remains as true. If what we do is we change switch to false in this for loop, and if there is a swap here, we'll change switch to true, which will tell us that there was a swap in this round. So next time when I come and check if there was a swap, I will go for the second round. Okay, so this is for switched. Then passes, how many passes you have? We are going to have 5 passes. Okay, and pass plus plus, that is your simple for loop for 5 passes in case of n equal to 5, 0 to n minus 1. And here if you see the inner for loop, it has to be, we have to compare adjacent elements. So this goes from 0 to, it should be ideally 0 to n minus 1. But why I have put 0 to n minus pass minus 1? That is because I am using the improvised version of bubble sort, and in the first pass, when pass is 0, j goes from 0 to n minus 1. But when pass is 1, j will go from 0 to n minus 2. Why? Because I know that the last element is already at its proper location. I don't need to compare with that. So you will compare adjacent elements here, and if you go inside this for loop, you are turning your switch to true, and this is just a swap operation. You swap the elements in case they are not in proper order, and then you come out. Once you're done with this inner for loop, you will go back to this for loop and you will repeat this 5 times, and that will sort your array. So this is what I was telling you. This is the improvisation. I don't need to go from 0 to n minus 1 in every round. I know elements, the maximum element is shifted towards the end in every round, so I can cut down on my comparisons in case of the inner loop. Okay, so this is your bubble sort. You must have probably done it in your C programming course to sort. This is a simple algorithm with a double for loop. Now there are two more algorithms which I used for sorting. What is an algorithm? This is the sequence of steps you follow to get some work done. So the work here is sorting. We want to sort elements. So we want to sort, that is our problem, and there are different ways we are sorting. Heap sort was one method, then bubble sort is another method, third one is insertion sort. So what is the insertion sort and how does it work? So if you can remember it this way. Okay, insertion means if you are given a list of elements to sort, you will pick up the first element and put it at its proper location. So in every round, in this case, we just take care of one element at a time. So you can look at it like this. If you have in the first pass, which is pass 0, I have 34. With respect to your p plus 1 elements. How many elements? P plus 1. P is 0, so p plus 1 is 1. So there's only one element. 34 with respect to itself is sorted. Okay, but when p is equal to 1, you are actually taking care of the first element. Is 8 sorted with respect to the first p plus 1 elements? P is 1. P plus 1 elements is first two elements. Is 8 sorted with respect to first two elements? No. So you pick up 8 and see where you can put it. This is the rough way of describing this algorithm. We'll see how we'll do it in the programming. So you shift 8 to its proper location with respect to 34. So we're just considering p plus 1 elements. Okay. In the next round, we will consider, we're talking about this round, but this is the sorted array. So in before p equal to 2, we pick up 64 and we say, okay, can 64 go at the first location? No. Can 64 go at the second location? No. So 64 was at its proper location with respect to first p plus 1 elements, which is 2 plus 1. With respect to first three elements, 64 was already at its proper location. So next you take 51. So 51 is greater than 8, greater than 34. It is less than 64. So 51 will take place of 64. So it's like picking up 32 and looking for the proper place to put 32. So the proper place is before 34. And if you see in the next pass, that is what we are doing. Okay, then you take 21 and in this pass you find the proper location of 21, that is before 32, that is here. So you insertion sort, pick up the first element, it is sorted with respect to itself. Pick up the second element, see if it is sorted with respect to the first element. Pick up the third element, see where it can fit between. You check on your left side where this element can go. Okay, and how do we do it in programming? So we start with p equal to 1 to n. Okay, the element that we are considering, for example, we are considering let's made up this off. So I'm considering when pass is 1, so 34 is already sorted, so pass 0 does not matter, so we are taking 8. Okay, we are putting 8 in temp, so temp has 8. Okay, j is equal to p, j is 1, j is greater than 0, so j will go from 1 to 0 because I'm doing j minus minus. So I'll compare 8 with all the elements on its left. So if the element on the left of 8 is greater than the element in temp, which is 8, so 34 is greater than 8, we will put 34 in place of 8. So we are overwriting 8, but we have saved 8 already in temp. And j minus minus, j is 0, so j greater than 0, it comes out of the loop and it puts 8 in your aj. So j is now 0. So 8 goes in the first location. So let's run it for some other, let's say 64. Let's take 51. So p is equal to 3. I've written the pass numbers here 0, 1 and 2, but passes start with 1 and 1, 2 and 3. Okay. When you take 51, put it in temp, is 51 greater than 51 less than 8? No. Is 51 less than 34? No. Is 51 less than 64? Yes. So if 51 is less than, so this will continue till your 51 is less than the elements on its left. So actually it will not start this way, it will start this way. It will first compare with 64. So is 51 less than 64? Yes. So what it does, it shifts your j is p. So in the location of 51, it shifts the 64 in place of 51. So it's actually moves 64 here, and then it checks, is 51 less than 34? 51 is not less than 34, so it comes out, and in now your j is gone one down, so it was 3, now it is 2, so it will put 51 here. Okay, so that is your insertion sort. Now another sort that we have is selection sort, kind of similar to what we do in case of bubble sort, but in bubble sort we compare adjacent elements so that the maximum is shifted to the right. Here what we do is we scan the array and we pick the largest entry and we place it at the end of the array. So how do we place? We exchange it with the largest element. So I'll just go straight away here. So I start from the last location. Current should be greater than 0 till the first location, current minus minus. Select maximum of L. L is the array, so you select the maximum of the array. Swap maximum with current. Current was the last element, okay? Then you swap those and you continue. Now current will be max minus 2. Now you will select the max of L. You will, when you say this L, the select max L should also take the left and the right limits of the array, in the sense now the max element is at location max minus 1. Next time we have to leave out that element which we have just played, so it will be max minus 2. So we'll scan from 0 to n minus 2, find the maximum, put it in n minus 2. Then we'll scan from 0 to n minus 3, find the maximum, put it in n minus 3. Now your limit is 0 to n minus 4, and so on. So scan 0 to second last element and pick the largest and place it with the last element of the block, which is the second last. When you're going from 0 to second last element, we are exchanging it there. Okay, and you will continue. So you will go from max minus 1 to 0. So your block will be first n size. You'll find the maximum element in this and exchange it with the last element. Okay. Then you find the maximum element in the block 0 to with only n minus 1 elements, which is 0 to n minus 2, and put it at the last location of the block, and so on. So select the maximum. The selection sort means select the maximum element, put it at the last place. Then go and for the rest of the array 0 to n minus 2, select the maximum, put it at the last location of that block, and continue. Okay, I haven't written swap and select max, which you can do. You can also pass the left and the right limits of your array in this select max. So it's like this. Let's do an example. This is my unsorted list that has been given. I don't have anything in the sorted sublist, and I scan, I find 64 is the maximum element, so I put 64 here, basically putting 64 at the last location, and then I'm left with the rest of the elements. Here the maximum of these is 25, then I put it as the second last element of the list. Then my next maximum is 22, it will be in the second last. Then my block is only 11 and 12. Okay, then okay, then 11, 12, 12 comes here, and 11. In fact, just a second. When you put this 64 in this sorted list, then 64 is here. You are left with this. You find the maximum. It is 25. So actually, according to, this is just a rough example, but according to our method of swapping, 22 and 25 are swapped. So this should be 22 and this should be 12. Okay, so you'll swap the maximum element with the last element. Okay, and this is how we have done it. You can do it this way also, but according to the logic that I've explained earlier, we will swap the maximum element with the last element. So 25 will come here, then we'll put it in the sorted list here, and then we'll be left with 11, 22 and 12. Okay, then between from 11, 22 and 12, it is 22 is the maximum, so it will go here. Basically you'll swap 22 with 12, so 22 will be your third element and 11 and 12 will be first two. And when you get 12, it's already the maximum. You'll continue, and like I've mentioned here, so we will swap 25 and 22, and we'll be left with 11, 22 and 12, and so on. This is according, this one is not according to our algo. This example here is according to our algo. So your right hand side will be your sorted sublist, and your left hand side is the unsorted sublist, because we are dealing with blocks. Okay, so that was your sort number 4. Now the next sorting algorithm that is there is known as Shellsort. So what we'll do is we'll actually the example for Shellsort, I will run it using a program most likely. So the difference between Shellsort and Insertion Sort that we did, when we did Insertion Sort, we picked up an element and compared it to all the elements on its left, and saw and checked where it could fit properly and put it there, inserted it there. So here, so we were comparing, let's say, element at 2 with element at 1 and 0. We were comparing element at 3 with element at 2, 1 and 0, and so on, to every element on the left. So with a gap of 1, what I mean by gap of 1, so you have elements at, okay, let's go back to some example. So in case of, this is your selection sort, in case of insertion sort, so I'm comparing 8 with 34, Okay, then when I take 64, I'll compare 64 with 34 and 64 with 8. Okay, then when I take 51, I'll compare 51 with 54 and 51 with 34. In this case, if 51 is greater than 34, then we will stop the algo there. Okay, so you compare, what I want to show is, let's say 51 is compared to 8. So you compare with the element at a distance of 1, you compare with the element at a distance of 2, you compare with element at a distance of 3. In case of insertion sort, you compare the elements which are away from your element in consideration and then see if they are sorted with respect to each other, and if not, then you swap or shift them. In case of shell sort, at any point of time we have a edge sorted array. What we mean by that is that all the sublists of every hth element is sorted. So all the elements which are placed apart by a particular distance, which is given by h, they are sorted. So you first sort elements which are at a distance of, let's say, 4 with respect to each other. Then you sort elements which are at a distance of 2. Then elements at a distance of 1 till you get a completely sorted array. Okay. So this is a bit complicated to explain. I will do it at the end of the lecture with a running program with this algorithm, and we'll see what we mean by shell sort and incremental distances and incremental how elements at a particular distance are sorted. And when you do it for n and distances of n by 2, n by 4, how your array gets sorted completely at the end. Okay, so let's skip that for now. Let's finish our sorting algorithms. Then you have bucket sort. It's a very simple sorting algorithm. What you do is you you have different buckets. Let's say sometimes when we have to sort uh, let's say currency notes, you have different currency notes, so you put them all in different piles and then sort each pile individually. Okay, uh, you can do it for different things. Okay, so for example, if you have numbers, I normally when I sort your papers, uh, I have roll numbers, let's say 0 to 50, so I have to sort them in order. So currency, maybe you don't have those many options, so let's take your answer books, and I have 0 to 50 roll number, sorry, 1 to 50 roll numbers. So as when I have to sort them, I make 5 piles. So in the first pile I put all the roll numbers from 1 to 9, then second pile I put all the roll numbers from 10 to 19, but they're not yet sorted. Whenever I encounter something between 10 and 19, I put it in the second pile. Similarly, third pile, I'll put um, roll numbers between 20 and 29. Similarly, 30 and 39, 40 and 49, and 50. Then I have these 10 papers or 9 papers in one pile. Then I sort them. Okay, then I sort them whichever way I want. Okay, so that is the bucket method of sorting. So if you have these numbers, all the numbers from 0 to 9 I'll put in this bucket, just like sorting your papers. 10 to 19 I put here, 20 to 29, 30 to 39, 40 to 49. So some buckets are empty and some buckets have more than one element. If there's only one element, it is already sorted. So this one has more than one element, so I can sort this bucket with any sorting algorithm that I like. And once they are sorted, you just have to place all the buckets in sequence and you get the sorted array in the end. You can apply bucket sort again on this, which is your wish, or any other sorting algorithm. Okay, so a little bit about complexity, which you will read more about in the next semester. Your the number of buckets you have will define basically how much extra work you have to do when you have to sort. If you have only 3 buckets, it is easy. When you have 10 buckets, it gets more complicated. You have to reserve more space, take care of more buckets. So you can just imagine it like that for now, that it is more complicated if you have more buckets. And it also depends on what kind of input you're getting. Maybe your input is such that only one bucket is filled, then the whole purpose of bucket sort is lost. If everything goes in one bucket, then you have to sort the same n number of elements in within that bucket sort, so bucket sort will not help there. Then the next one is Radix Sort. Radix Sort, we're not doing programming for bucket sort and Radix Sort, and mostly not only also for Shellsort. That I'm just asking you. So that's why I might do a running program for that. Otherwise, okay. So your next one is Radix Sort. So Radix Sort, you don't compare anything. You sort by the rightmost digit. So your rightmost digits will be sorted. So you basically sort from the ones place. Whatever is less comes first. So 0, then 2, then 5, and then 6. Then you sort by tens place. So it's not, you don't sort within a bucket, you sort it overall. So based on tens place, you have 0 in case of 2-digit numbers. 0 here, 0 here. Okay. You also have 0 here. So this kind of stays the same here if you see. Then you have 4, then you have 6, then you have 170 for 7 for tens, and 90. Then when you sort by hundreds, everything falls in order. I've written it in 3 digits so that you can see, and I've underlined based on which digit we are sorting this. Okay, so simple. This is called Radix Sort. Now the main two sorting algorithms that you will be studying a lot in your algorithms is Mergesort and Quicksort. So your Mergesort is a kind of problem solving technique where you try to solve a problem by first solving the same problem but of smaller size. So if I give you one element and I ask you to sort it, you say it is already sorted. If I give you 2 elements, then let's say you say, oh, let me break it into 2 parts. So I give you 10 and 11. You break it into 2 parts. 10 in itself is sorted, 11 in itself is sorted. But now you have to sort these two together. So you compare the two, or you combine the two, and when you combine, you make sure that you combine them in proper order. Okay. So that is why this is known as merge sort. So what we do is, if you have an array to sort, you break it down. So first I break it down into 2 halves, which is a smaller problem than a problem of sorting 8 elements. Now I have 2 problems of sorting 4 elements. I break it down further, each at their own level. So now I have 2 problems on the left of size 2 and 2. If you look at it, it looks like a binary tree. So on the right also, this is broken down into 2 problems of size 2 each. Then I further break them down to a problem of size 1. So this is the basic problem. When you are given a sorting problem, what is, we call it the base case. Like in induction, you call the base case. So the base case is you have one element, it is already sorted. But then we try to combine these two. The leaf nodes to form the root node, but in proper order. So 1 and 13 is already sorted. So when we combine, we put them together. 24, 26 already sorted, you put them together. 2 and 15 already sorted, you put them together in the same way. 27, 38, this is 38. Okay, I have written 28, so let it be 28 for now. So there's a correction here. So let's make it 28 because I've continued with that. Now you have four problems of 2 size. We are trying to merge it again. So when I merge 1, 13, 24, 26, it is already in order, so it will be merged in order, and same here. If it was not in order, we would have to do comparisons, which I'll show you here how we do it. So I've actually marked arrows and numbered them how we compare. We first compare first element of the left side with the first element of the right side. If we are doing ascending order, whichever is lower goes here. So 1 goes here. So this pointer moves ahead. This pointer stays where it is. So you compare 13 with 2. 2 is smaller, so 2 comes here. So this pointer moves. The right hand side pointer moves. Then you have 13 and 15. 13 is smaller, so 13 comes here. So this pointer moves ahead. And this pointer stays. Then 24 and 15 are compared. And 15 comes here because it is smaller, so this pointer moves ahead. Now you have 24 and 27. 24 is smaller, it will come here, and this pointer will move ahead. 26 and 27. 26 is smaller, it will come here, and this pointer moves ahead. Basically, you are at the end of the left hand side, so you know whatever is after this, whatever is at this point and beyond it is already sorted, because when we were merging we were sorting them as well. So you can just append the rest of the right hand side here and you are done, and it is the sorted array. Okay, now how do we do it? How do we divide? We find the center point of the array. It's a recursive method of solving a problem. So I want to sort a array of size 8. I will divide it into 2 problems of size 4 each and apply the same merge sort algorithm on it till you go to the base case. So if left is less than right, that will happen only when there are more than one element. If there's only one element, it will be the end of that chain. So center is left plus right by 2. You call merge sort on the left hand side, you call merge sort on the right hand side, and once both return, you will merge them. And what is merge? Merge is basically this, what we were doing here, the comparisons I have mentioned with arrows. Okay, and what is merge? That is the main issue here. How do we merge? So if your left pointer is less than your right pointer, the left pointer goes in the temp array. Okay, and you have to maintain the position. Basically there's a pointer here as well. So when there was when you added 1, the pointer was here. Then when you added 2, pointer is here. So we have to do this, increment it as well once you put an element. If its left pointer is not less than right pointer, then the right side goes into the final. Temp array is basically the final array where you're storing your sorted array. And this will continue while left pointer does not reach its end or right pointer doesn't reach its end. Basically, from the end means for left pointer the end is here, and for right pointer the end is here. Right pointer starts from here, left pointer starts from here. Now if left pointer comes to an end, left or right pointer, one of these two can come to an end at before the other, which happened in our case. Left pointer, it reached its end, so right pointer still has some elements. So accordingly, if there is something left in the left hand side, you will just straight away add them to the temporary array, and if there are some items left in the right hand side, you will just end. This is one of the 2 cases might be true, so it will go either here or it will go either here. So after merging these two, what we are doing, we are taking everything from the temporary array and putting it in the main array. Why? Because when you are merging at this level, we are making the changes, we want to make the changes within the main array itself, so that when we are comparing, we actually compare based on the left and the right pointer. Okay, and we are passing a, and we are passing this temp array also, and then we copy it back to a so that we have the final answer in a. So if you see, I have put 38 again here, so we will go based on that. I already showed you how the pointer moves. Your temp position pointer also moves when something is added. Okay, so that is your merge sort. Now a similar algorithm where we again use recursive method and divide method, that is dividing the problem into problems of smaller size so that they are easier to solve. So that is known as quicksort. So in case of merge sort, we divide the array without thinking what is in the left array and what is in the right array. We leave that job of actually sorting to the merge function. In case of quicksort, we don't just divide the array. We divide the array based on some logic so that we don't have to merge it in the end. So what is the logic? Quicksort picks up an element from the array or from outside the array or any random number which we call as the pivot. Okay, this pivot is a number to which you will compare all the numbers in your array, and if your numbers are smaller than this element, this pivot, then they'll go to the left subdivision, and if they are greater, they'll go to the right subdivision. So before I go to the code, I want you to show this example. So this is my array, and I pick up, let's say I pick up the middle element or some element 65 as my pivot. So everything less than 65 goes to the left, and everything greater than 65 goes to the right. So right now I'm just sending everything roughly based on their order of occurrence in the array to the left of 65, and everything greater to the right of 65. So basically 65 at this point after the first round is at its proper position where it should be in the sorted array. Now I want to sort the left hand side. So again I select a pivot again in the left hand side, and in the right hand side again I select a pivot. This pivot 92 is meant for the right hand side, 31 is meant for the left hand side. Okay, this is your left hand side, and this onwards is your right hand side. So based on 31, all the elements smaller than 31 go to the left, greater than 31 go to the right. Similarly, 92, smaller than 92 go to the left, and there's nothing greater than 92 go to the right. So I mentioned which parts are already sorted. Now again you have a, we select 26 as pivot, smaller than 26 goes to the left, greater than, there's nothing, so all of this is pretty much sorted. When you select a pivot 81, 75, they go in order and they are sorted. Okay, then I'm left with 0 and 13. If one of them is selected the pivot, let's say 0, then they will be sorted. Okay, so this is the rough way of doing quick sort. But when we write a program, we cannot just randomly shift elements right and left. You need a proper procedure. So what we do is, you imagine two pointers I and j. So I is pointing, let's say, to -1 for now, and j is pointing to the last element. Now your last element for now in this case has been selected as the pivot. So what do we need to do? We need to put all the elements less than 40 on the left hand side and all the elements greater than 40 on the right hand side. So the logic goes like this. I which is a pointer, it will keep on moving rightwards. It will keep on moving rightwards as long as the elements it encounters are less than 40. Once it encounters something which is greater than 40, it will stop. So you see I've mentioned the first stop of I is here. 81 is greater than 40. Similarly, J will keep on moving left as long as it encounters elements which are greater than 40. As soon as it encounters something less than 40, it will stop. So now I and J have stopped. So I has the element which is greater than 40, J has the element which is less than 40. So I will swap the two so that they can move ahead now. I and J pointers can move ahead in their respective directions. So now I have swapped 26 and 81. So after that, again J will move leftwards till it finds an element which is less than 40, and I will move rightwards till it finds an element which is greater than 40. So again they have stopped, and I will swap the two. Okay, after swapping, this is my I was here. It will keep moving rightwards till it finds something which is greater than 40. So I stops here, but J was here. Okay, it moved leftwards and it found 31 which is less than 40, and it actually crossed I. Okay, so J has reached here and it has crossed I. So if it has crossed I, okay, that means now whenever this crossover happens and I has stopped here, we swap I with the pivot or the rightmost element. So after this we get this, and now these are the two subdivisions in case of quicksort. So in case of merge sort, because we divide the array into two equal parts, in case of quicksort we don't know, based on the pivot element we would not know whether we'll get an exact 50-50 division or any other division. Sometimes the ratio can be very bad. You can have nothing in the left hand side and you can have everything in the right partition. So you will study more in detail about that in your next class in the next semester. But for now we got a pretty much okay division, and now we have to do the same thing again. So you select a pivot. Let's say 31 is our pivot here, and again do the same thing. I moves rightwards, J moves leftwards. I will move all the way till here, and then it will be sorted, and same procedure applied here. Now 43 is my pivot. I and J, so it will, I have just noted down what will happen. I moves here, your pivot is 43, so all the elements, when J starts moving leftwards, all the elements are greater than 40, so J will cross over I and you will swap, and this is your final. Then see, this time you did not get any left division here, you just have the right partition. You select 65 as the pivot, okay, and based on that again I and J will move, and you will, there's a crossover again, and 65 will come here. Then you left side is already sorted, and you select 92. Again J reaches here and I reaches here. There's a crossover, so you get 92 here and 81 75, and they will be sorted to 75 81. Okay, so this is your quick sort. So how does it this happen in case of, in terms of the programming? So you, in our case we are selecting the pivot as the rightmost element. I is left -1, so we set it to -1. J is right, so this is an empty loop. It will break only when I and J cross over. Okay, so while Okay, I forgot to write. This has to be A plus plus I and A minus minus J. While these elements are, this is just the I pointer moving rightwards, plus plus I, and this is the J pointer moving leftwards. If I is less than J, that means if once they stop and I is less than J, you swap the two elements, else you break. And if you break, then you swap I with the rightmost element. Okay, and then you get two partitions based on your I value, and then you quick sort the two, and the same will happen, which I have explained in the example below. Okay, so there is a correction here, just have to put A here. So this is your quick sort. So I've tried to put many comments and arrows and colors so that you can see clearly what is exactly happening in every pass and in every partition. So remember, pivot is something which you can select based on your own logic or method or your assumption about the input data. If you think input data is going to be of this type, then you can, to have even partitions, you can select a pivot element accordingly. Okay, so I'll make the correction here before I post these notes. And if you have any questions, you can leave them in the comments. Shellsort, Radix Sort, and Bucket Sort. Don't worry about the programming part. You should just know how to do that sorting. Okay. If I get time, we will do a run of a Shellsort program separately. So this covers your sorting techniques, and I have mentioned all of these. For except for Shellsort, you should know the logic, the working like this. Like I have done examples for each, for every sorting algorithm, and coding for every sorting algorithm except for Radix, Bucket, and Shellsort. Okay, so we'll do some in our lab exercises as well so that you can see sorting actually taking place. Okay, so that is it for your sorting techniques. We are left with hash tables and graphs, and we'll see how much we can cover in them. Graphs, there's a lot to do, but we don't do everything in this course. We'll do limited in this course, and rest we'll cover in your algorithms course next semester. All right, let me end it here. Thank you. Bye bye.